In this video, we're going to continue discussing the final exam review for Calculus 1. And rather than going through all of the solutions to these particular examples, I think we'll just talk about the techniques necessary for each. Since a significant amount of time was spent learning derivative rules and using derivative rules, I don't think it's necessary to run through all of them again here. If you do have questions on the techniques, though, by all means reach out to me and I'll see what I can do to help. Now in this first example A, and I recognize that there are some duplicate naming here, so my apologies for that. We'll work through it. In this first A value, I think the chain rule would be appropriate here. It's not really worthwhile to write this out 5 times and multiply it together, so I would recommend using the chain rule here. For part B, you could use the chain rule by considering this expression raised to the negative first power. That would be fine, or most likely students will end up using the quotient rule here. For part C, I think the chain rule would be appropriate again, but let's remind ourselves that 2x to the third power plus 1 when inside of a radical could also be considered as that same expression raised to the power of 1/3. If you see it that way, then the chain rule becomes pretty easy or pretty straightforward method for finding its derivative. For part D, you have 2 options. You could use the chain along with the quotient rule, or again, you might recognize that this square root implies that we're talking about a 1/2 power. And since that 1/2 power is in the denominator, you might think of this as 4 minus x to the negative 1/2 power. And from here, I would then use the chain rule. So a little bit of algebra setting up the expression makes it a fair bit easier in computing the derivative. For this one, I think using the quotient rule would be appropriate. You can find the derivative of the numerator using a mini chain rule and the derivative of the denominator as well, and use both of those denominators within the quotient rule. For this example, I know there's going to be a tendency to distribute this x into the grouping symbol, but remember you can't do that until you complete the exponent step first, right? You can't multiply within an expression until the exponents are all finished. So if you wanted to distribute this, then you must cube this binomial expression first and then distribute your x value in. For that reason, I think the product rule would be better to use this time, because you've got a first function and a second function. The second function is going to require the chain rule to find its derivative, but that I think is better than the alternative of distributing and multiplying this out before you compute any derivatives. I think the product rule would be appropriate for this question as well as this one, treating the first and second functions as such. And then lastly, quotient rule. Although sometimes these trigonometric expressions, if you utilize trig identities, you might be able to simplify this and eliminate the quotient. That's not the case here. We don't have any exponents. If we had sine squared or cosine squared, we might be able to use a trig identity to rewrite this expression. We don't have that, so I think the quotient rule would be appropriate there and here as well. And so again, while working on those derivatives on your own, please let me know if you have any questions and I'll explain them a little bit further as far as the solutions, how they're obtained. Moving on to this question. Now, this is the second time we've seen a problem like this. In fact, the first time was just at the very end of the last video, where we're given a point and we need to establish the equation of the tangent line. So we'll go ahead and work through this one here. Now what makes this one a little bit different is that our equation is written with both x and y variables, so we have to use implicit differentiation this time. And that's just where we use mini chain rules to find the derivatives with respect to y. The derivatives of y with respect to x. So as we discussed in class way back in Unit 3, essentially what we're doing is we're taking the derivative with respect to one variable, whether it's x or y, it doesn't really matter, but most of the time we do use x. And when we encounter a derivative that's not regularly computed, well, we'll leave the differential alone and then we'll work with it as a variable. So the derivative of x to the fourth would be 4x cubed, no problem. The derivative of 2y squared would be 4y, but that's the derivative of y with respect to y. If it's the derivative with respect to x, we don't really know what that is, so we're going to tack on this extra differential, dy dx, and that essentially completes the chain rule where we have the outer function 2y squared, 2 times something squared, and the inner function is y, so the dy dx shows up as part of the derivative there. For this last component, for y, the derivative of that would be 4 if we were deriving with respect to y, but since it's with respect to x, we've got to include that differential dy dx. And now the derivative of any constant with respect to x is still 0. So we're going to subtract the 4x cubed to the right-hand side and factor out dy dx into the remaining, or from the remaining terms. So dy dx is going to multiply by 4y plus 4, and that's going to equal negative 4x cubed. And so lastly, when we isolate dy dx, the derivative of y with respect to x, we have negative 4x cubed divided by 4 times y plus 1. And I'm writing this as a common factor removed so that we can eliminate it and we can work with this expression as written. And so with this expression, we can now evaluate it at the location 2, 1. So dy dx is being evaluated at an x value of 2 and a y value of 1. So this vertical bar can be used to indicate that. And we would now have negative 1 cubed over, the x value was 2, so negative 2 cubed over 1 plus 1, which ends up being negative 8 over 2, or in other words, negative 4. So it appears that the slope of the tangent line is negative 4, and upon further review, that's all that this question was really asking, is to find the slope of the tangent line. But it doesn't hurt to take this a step further. If we're being asked to find the equation of the tangent line, so if this said find the equation of the tangent line through that point, we can take it a step further. That would be y minus y2 equals m times x minus x2, or x1, y1, whatever you want to call it. This is our point slope formula, where the y2 or y1 is the y variable or y component of the point. So we've got 1, and m we calculated out to be negative 4, and x2 is the x component of the coordinate, and now we can simplify. Negative 4x plus 8, y equals negative 4x plus 9. That would be the linear equation through this point on this particular graph. I almost called it a function, but I don't think it would pass the vertical line test. So the graph represented by this relation has a tangent line of this form, and it goes through this particular point. Now moving on to the next question, this is another one about derivatives. This time we're talking about second derivatives. And we would like to know where on this graph is the second derivative negative. Now if I'm looking at this graph, I would say that the second derivative is negative right here. And also right here at B and E. And I claim that these two are both locations where the graph is has a second derivative that's negative because the graph itself is concave down. A negative second derivative means that the graph is concave down. That means our rate of change is decreasing. And so while we have a positive slope through here, that's okay. The fact that the slope is decreasing is what's telling me that we're concave down. Same here, we have a negative slope that continues to be negative, but it's more negative as we move from left to right. So our slope is decreasing. When the rate of change is decreasing, that's telling me that the second derivative is negative. Now the opposite would be true if we're concave up, like at D and A, because in both of these cases the slopes are increasing as we move from left to right. So we got a negative slope becomes more positive and more positive and more positive still. So those are all concave up. The point at which the second derivative is negative, where the second derivative is equal to 0, usually occurs at an inflection point, although it doesn't always occur at an inflection point. In this case it does, because it looks like we're going from a negative second derivative. So our second derivative is less than 0 in this region, and then the second derivative is positive in this region. And so when we switch from a negative second derivative to a positive, that point of transition, the second derivative must be equal to 0, or is equal to 0 in this case. And so that's what I would indicate as my explanation. I would say that at point C we have an inflection point. That helps, but it's not the only reason. Primarily, though, we're changing or transitioning from concave down to concave up. And it's this change from negative concavity to positive concavity that implies that we've reached a point of 0 concavity along the way, in between. Now, question number 8 on page 5 doesn't have any instructions with it, but it looks like we have to answer a lot of questions about the function. Now, keep in mind we don't have a graph to look at, so we've got to perform all of this analysis using appropriate calculus skills. And so in most of these examples, when we're analyzing the graph, I would utilize the derivative tests, both first and second derivatives. So let's start by finding the first derivative. Y prime in this case, well, it looks like we're going to need a product and chain rule here. The derivative of the first function is 1 times the second function plus the first function times the derivative of the second. Now the derivative of the second does require the chain rule, but it's not too bad because the derivative of the outside, 4 times something cubed, times the derivative of the inside, well, that inside derivative is just 1. Now it would be worthwhile to simplify this, and we have x minus 5 to the 4th power plus, and this is kind of interesting, 4x times x minus 5 to the 3rd power. So I've multiplied these products, x, 4, and 1. Those can be multiplied together, and that's where the 4x came from. But now we've got x minus 5 as a common factor between these two terms. And so it looks like we can factor out x minus 5 3 times from both of those. And that leaves us with x minus 5 to the 1st power plus 4x. And if we clean this up just a little bit more, we've got x minus 5 cubed times, and see these like terms, 1x plus 4x makes 5x minus 5. Or I guess better still, we can factor out a common factor of 5 now. X minus 5 cubed times x minus 1. Now, having the factored form of our derivative helps me out a bunch because we often interpret when that derivative is equal to 0, and as it turns out in this case, because we have the factored form, we can see that this derivative will equal 0 when x is equal to 5 and when x is equal to 1. When either of these factors turn equal to 1, then the graph itself is equal to 1, or equal to 0. Let me back up, I may have misspoke. When either of these factors are equal to 0, then the entire expression is equal to 0. Now, there are 2 points that I'd like to investigate that tells me a little bit about the behavior of this graph. But also I want to note here that there's a multiplicity of 3. So if I'm thinking about the actual shape and picture of this graph, I ought to know what that means. We'll come back to that in just a minute. When x is equal to 1 and when x is equal to 5, we know that the first derivative is equal to 0. And so we often use test points to imagine what's happening in between those or outside of those two positions. Now, if I were to use a test point somewhere to the left of 1, say 0, then the derivative when x is equal to 0 would be something like this: 5 times a negative number cubed times another negative number. And that tells me that the slopes in this region are all going to be positive. If I were to pick a number between 1 and 5, well, again, I would get a negative number cubed. But in the second region, any number between 1 and 5, when subtracting 1, is going to give me a positive number. So that's going to give me a negative result in that region. And then lastly, if I pick a value bigger than 5, well, that's going to give me a positive number in this region. And a positive number cubed times another positive number times 5 will also leave me with a positive result. So I don't know a whole lot, or I don't know everything about the graph at this point, but what I do know is that the graph itself it's increasing in this region, it's decreasing in this region, and then it's increasing again in this region. And at these 2 points, at x equals 1 and at x equals 5, we know the graph has a slope of 0. So we can answer a lot of the questions over here on the left-hand side, maybe not all of them, but we know that it's increasing between from negative infinity up to 1. So we would say something like this: it's increasing on the interval from negative infinity to 1. It's but it also increases again from 5 to positive infinity. It is decreasing on the domain, or on the x values, from 1 to 5. There's going to be a local minimum or a low spot, we can tell now, at x equals 5. And I think that would be sufficient for this answer. I don't know that we need to include the coordinate. If the instructions are specific and they want you to include the coordinate, well, we can plug in 5 to this expression here and run with that. There's a local maximum at x equals 1. Now, as far as absolute minimum and absolute maximum, I would argue that there are none. And we can make that claim here because, well, this graph is continuously decreasing as we move to the left. It was increasing as we move to the right. And then over here, it's continuously increasing towards the right. There's no boundary to the high or the low points. So we would say that there are none, no maximum or absolute max or absolute minimum values. If we had, if we were told that this graph only exists on a particular domain, if there were endpoints, then we would check them for our absolute minimum and absolute max. But I think that's all that we can do with our first derivative, so we better switch to our second derivative or compute our second derivative next in order to answer the remaining questions. So I'm going to work with the derivative as it's written here. Let's say that y prime was 5 times x minus 5 cubed times x minus 1. I'm going to treat this 5 as a constant, so we'll just kind of report it. But as far as the second derivative goes, it's going to be 5 times, and then it's the derivative of this remaining component. And I'm going to use the product rule here. So we've got the first function and the second function as indicated. So the derivative of the first function is going to be 3 times x minus 5 squared times 1. So that's the derivative of the first times the second function plus the first function, x minus 5 cubed, times the derivative of the second. And it would be helpful to clean this up just a little bit, so I'll leave this 5 alone as it is. This times 1 doesn't need to be there, and this times 1 doesn't need to be there either. So we basically have 3 times x minus 5 squared times x minus 1 plus x minus 5 cubed. And in a similar sense to what we had in the prior example, we've got this 5. We've got this x minus 5 and x minus 5 that's acting as a common factor in that group. So I'm going to factor it out. We'll call this x minus 5 squared. And what's left behind is 3 times x minus 1 plus, and then there's one of these x minus 5s that's left over. And if we distribute and combine like terms, we've got this x minus 5 squared times now 3x minus 3. So that 3x plus x would be 4x. Negative 3 minus 5 might be minus 8. And there's a 4 that's common, so I'll factor it out all the way to the front. We'll call this 20 times x minus 5 squared times x minus 2. Now all along, we're computing our second derivative, and it would be helpful to know when completing our second derivative test when this is equal to 0. And it appears that our second derivative is equal to 0 when x is equal to 5 and when x is equal to 2. So again, we can use our second derivative test, much like the first, to answer some questions about concavity. And I'll try to draw this number line oriented in the same fashion that our first number line was written. So we've got 5, those two are directly over top of one another, and then now 2 that's just to the right of 1. And if I substitute the number 0 in place here, the second derivative would be equal to 20 times a negative number squared times another negative number, 0 minus 2 and 0 minus 5. But that's going to create a positive result here and a negative result here. So a positive number times a negative means that the second derivative is negative. And maybe I should be real clear about that. This is our second derivative test, and this was our first derivative test. If I pick a number between 2 and 5, let's say 3, well, 3 minus 5 still produces a negative result, but 3 minus 2 produces a positive result. So now we've got positive 20 times a positive number times another positive number. That implies that our second derivative is positive here. And then lastly, if I pick a number bigger than 5, let's say 6, well, now we're dealing with a positive number squared, another positive number. And the product of those three positive numbers is also positive. Now with the second derivative test only, we can answer questions like this. The function is going to be concave up, where the second derivative is positive. So that's concave up on all x values between 2 and infinity. So from 2 all the way to the right towards infinity, that's where the function is concave up. It's concave down from negative infinity up to the point 2. And there appears to be an inflection point at x equals 2. Remember, inflection points are where the concavity changes. And so the concavity was equal to 0 at x equals 5, but in actuality it's not appropriate to say that there's an inflection point at x equals 5 because the concavity did not change. So I think I may have messed that up in the answer key that I posted earlier. Concavity doesn't change, so therefore we would not call this an inflection point. If we're thinking about the shape of this graph, we have lots of information to interpret that now. Not only do we know the direction in which the graph appears to be traveling, but we also know a little bit more about its behavior. Now back to this back to the inflection, let me try that a third time, back to the multiplicity that occurs at 5 here. I had mentioned that while talking about the derivative, but I really should have been thinking about that in terms of our expression back here. There is a multiplicity at x equals 5 of 4. So the behavior of this function is going to be like a quartic graph at that position. And that hopefully clarifies what's exactly happening right here, how the concavity itself doesn't change. If we were going to sketch this graph on an XY axis, we might create something that looks like this. When x is 0, y ends up being 0 because there is no constant in our original function, so there's no constant here. But I noticed that when x is equal to 1, we have to have a high point in the graph. When x is equal to 2, our concavity has to change. And when x is equal to 5, we reach a low point in the graph, but the concavity itself does not change. So if I'm sketching this graph, I might have something that looks like this, where we're reaching a high point at x equals 1. We're starting to drop. And then at x equals 2, the concavity has to change. I've got to be a little bit more careful here. We're decreasing, but then the concavity starts to change. Then we reach a low point at x equals 5, which I happen to know to be a 0 here of the graph. This has a multiplicity of 4, so it must reach this, and within this tiny window it's going to look like a quartic graph, or almost a parabola. And then the function turns away from the x-axis and increases again. And so we would create this sketch if asked to do so, of course, without the use of a calculator. So some components that I'd be looking for while scoring this is your inflection point, whether that's in line with an x value of 2, whether you've got a maximum and a minimum point at 1 and 5. It would be helpful to have this coordinate, this 0, as well as this 0. And of course, the end behavior, the tails, must be correct as well. So we'll go ahead and stop this video here and pick up with page 6 of our review in the next one.